Okay, in this video we're going to work on the inventory control problems in section 2.6. So I'm looking at question number 3, and it says a pharmacist wants to establish an optimum inventory policy for a new antibiotic that requires refrigeration and storage. The pharmacist expects to sell 800 packages of this antibiotic at a steady rate during the next year. Okay, so that is 800 is the inventory, and that's going to equal R times X. R being the number of orders he places a year, and X the number of antibiotics in each order. She plans to place several orders of the same size spaced equally throughout the year. Okay, those orders are the R. The size they are is the X. The ordering cost for each delivery is $16. Okay, so $16 is the ordering cost for each delivery. So remember, your inventory cost is going to consist of an ordering cost plus the carrying cost. Carrying cost is the storing of the material you've ordered for the year. So the ordering cost is $16 per delivery. So that's going to be 16R. And carrying cost based on the average number, remember this is really important, the average number of packages in inventory amounts to $4 per year for one package. So it's going to be plus 4 times X, but since it's based on the average, I'm going to divide that X by 2. So now we have an equation for our cost. Okay, A, let X be the order quantity and R the number of orders placed during the year, and we have done that. Find the inventory cost, ordering costs plus carrying cost in terms of X and R. So this inventory cost is right here. Find the constraint function. Okay, the constraint function is right here. 800 equals R times X, because they're going to sell 800 packages of this antibiotic per year. Determine the economic order quantity that minimizes the inventory costs. Okay, so we want to minimize inventory costs. This is an optimization problem. Here is our objective function, which is our cost equation. And we need to use the constraint, which is up here, to have our objective function be written in terms of only one variable. So what I did was the following. I'm going to rewrite our cost in terms of the one variable, but in order to do that, I'm going to take this 800 equals Rx right here and say that 800 over X equals R. So now let's work on our cost equation so that it's in terms of only one variable. So cost is going to equal 16R plus, 4 over 2 is 2, so 2X. Okay, so that's still in terms of two variables. Take your R, which is right here, and I'm going to replace it with this, 800 over X. Okay, so now my cost equals 16 times 800 over X plus 2X. Okay, so clean that up. Cost is going to equal 16 times 800 is 12800. Okay, so 12,800. Bring up your X to the -1 plus 2X. Now take your first derivative, because remember we're going to optimize this. So you get -12800 X to the -2 plus 2. Set that equal to 0, and what you end up getting is that your X is going to equal 80. That makes your R, putting it back into the constraint, equals 10. Now we should just check your second derivative. Your second derivative would be, so 2 times 12,800, so that's 6 25, 0, 0, and then I have x to the negative 3. Okay, that's going to be a positive number. Since that's greater than 0, I know that my value of x is going to minimize my cost function because I'm concave up. Okay, so determine the economic order quantity that minimizes the inventory cost. So this is it. You're going to order 10 times a year with a quantity of 80. And that's your economic order quantity. So think about this. You should be able to repeat this and replace different variables as needed in these kinds of problems. Okay, we're going to go on to the next problem in just a sec. Alright, here's our next problem. This time we have a furniture store problem, but it's another inventory control problem. So let's look at this. So it says a furniture store expects to sell 640 sofas at a steady rate next year. So that means that the inventory they need for the year is going to be 640, and that's going to equal Rx or Rx. Okay? The manager of the store plans to order these sofas from the manufacturer by placing several orders, those will be the R's, of the same size, so the size will be X, spaced equally throughout the year. Okay, so this is our constraint right here. The ordering cost for each delivery is $160. Okay, let's start building our costs. We know that cost equals ordering costs plus carrying costs. So let me just make that a better C. So ordering cost plus carrying cost, and now we're giving us some data. The ordering cost for each delivery is $160. So delivery. So ordering cost is a delivery, so that's R. So I have $160 R plus, and carrying cost based on the average, okay, average number of sofas in inventory amounts to 32 per year for one sofa. So 32 times X, but because it's based on the average inventory, I'm going to divide that X by 2. So let's clean this up just another step. So cost is going to equal 160 plus 16 times X. All right. Let X be the order quantity and R the number of orders placed during the year. Find the inventory cost in terms of X and R. Okay, so that is your unadjusted objective function, and it's right there, and I need to put my or back on there. It's right there, so that satisfies A. Find the constraint function. Okay, the constraint function had to do with how much inventory they need to have for the whole year, and that's right there. Determine the economic order quantity that minimizes the inventory cost, and then find the minimum inventory cost. Okay, so now we're going to write our cost in only one variable. And let me just make this look a little better too. So I'm going to do that. I'm going to put my R here and my plus, and that looks like a cleaner equation. Okay, so given this opportunity, given this equation, we're going to have to write it in terms of only one variable. So you know how to do that. You're going to look at that equation and say, wait a second, I can use the constraint, and let's have R equals 640 over X. Okay, so my cost is going to be 160, and I said let's make R equal, so R equals 640 over X. So instead of having an R, I now have 640 over X, and then plus my 16X. So clean up that equation. 160 times 640 is 102400. Bring that X up, unless you want to use the quotient rule, which would be totally fine. Take your first derivative to optimize it. This is X to the negative 2 plus 16. Set that equal to 0, and you're going to say 1,02400 over x squared equals 16. And by solving that, you end up with x equals 6400. X squared equals 6400. So x will equal 80. And looking at my constraint, if x equals 80, plugging in 80, I will get r equal to 8. So let's see what the question is. Determine the economic order quantity. Okay, this is it. In order to minimize cost, they want to place 8 orders per year, and each are going to have 80 couches or sofas. Okay, that's the economic order quantity. 8 orders a year consisting of 80 sofas each. And that takes care of our next problem. Let's move on to problem number 5, which will be our third and our last inventory control problem. Okay, here is our third and last inventory control problem. So it says a California distributor of sporting equipment expects to sell 10,000 cases of tennis balls during the coming year at a steady rate. So here's your constraint, and it's going to be 10,000 equals R, number of orders placed during the year, times X, number of cases in each order. Yearly carrying cost is to be computed on the average number of cases in stock during the year. Okay, remember that average number means we're going to divide by 2. So let's set up carrying costs, or let's set up inventory costs. So costs equal the carrying cost plus the ordering cost. Okay, so they're telling us yearly carrying costs are going to be $10 per case, so 10x, but since it's based on the average number of cases, divide that by 2. And the cost of placing an order with the manufacturer is $80. So plus 80 times the number of orders placed. A, find the inventory cost incurred if the distributor orders 500 cases at a time during the year. Okay, that's not an optimization problem. So for A, they're telling you that you're going to be ordering 500 cases. So that means that your X equals 500. So if your X equals 500, can you figure out what your R is? So doing the math, you should be getting R equals 20. So 20 times 500 gives me the 10,000 I need to have in-house to sell for the year. So if I have those values, I'm not optimizing costs, I'm just plugging in and solving. So my cost is going to be, okay, 10 divided by 2 is 5. So 5x, and they're telling us that x is going to be 500, plus 2 times, and we figured out that 2 has to be 20. So without optimizing, just by using the figures they gave us, the cost is going to equal $29,100. Okay. Now let's go on and read the next part of the problem. Okay, B says determine the economic order quantity. That is the order quantity that minimizes the inventory cost. Okay, so now we're going to optimize. So we have to go back and do all the steps we normally do. So, number one thing, you're going to end up writing your R in terms of X. So take your constraint, and I will say from that constraint that R will equal 10,000 divided by X. So now let's take our cost equation and we're going to optimize it. So cost equals 5x plus 80r. Okay, write it in terms of one variable. Don't touch your x, but wherever you have an r, you're going to instead put 10,000 over x, or times x to the negative 1. Okay, do that math. We have 5x plus 80,000 times x to the negative 1 ends up being 800,000 times x to the negative 1. Now optimize the situation by taking the first derivative, and this is still going to be, whoops, excuse me, it's going to be a negative, minus 800,000 x to the negative 2. When you set this equal to 0 and solve for x, you're going to get x equals 400. Notice that they suggested in the first example that x equals 500, which is too big a number to order per time if you want to optimize or minimize your cost. So if x is 400, then r, plugging it into the constraint, ends up being 25. And that is the situation you want if you want to minimize your cost. Okay? And that's the last problem. So you should have a better understanding of this, but if you need to, go back and listen to the explanation again and make sure that you can do this on your own.